We can now go to the next question in the extra classwork sheet, which is question number 12. Now this question is again related to question number 10. I'll just read it. Question number 12, a ladder. So now it's an actual ladder. It could be a rod, of course. It won't make any difference in the question. You will see that a ladder rests against the rough floor. So now you're returning to the conditions of question number 10, where the floor is rough and a smooth wall. So this is smooth. A ladder rests against such two surfaces so that slipping impends. So it's in limiting equilibrium, impending slipping. Now that would mean that this theta, we have already calculated it, it has to necessarily be equal to tan inverse of 1 upon 2 mu. This was exactly what we did in question number 10. When slipping impends under such conditions, the angle theta is tan inverse of 1 upon 2 mu. So theta is fixed now. You're not going to change theta. Remember, the weight of the ladder acts at the midpoint, so that's going to be over here. It's W. These two distances are L by 2 each, and the ladder is in limiting static equilibrium. And now there is an added complication in this problem, namely that there is a man who is trying to ascend the ladder. So let's place him somewhere over here. Let's say he's on the ladder and his weight is W dash, and we have to find what is the maximum distance he can ascend the ladder. So how far can he go up in this direction without disturbing the equilibrium? So the implication is, as the man climbs further and further, at some stage limiting equilibrium conditions will prevail, and we have to find at what distance this happens. Now once again, if you can use your intuition, perhaps if you place a man at this point and if you place him at the bottom of the ladder, most of you, your intuition will tell you correctly that the fellow who is at the bottom, if in a certain case a man stands on the ladder but at the bottom, near to the bottom, then this situation is safer than somebody standing at the top. The ladder is more likely to slide when the person is on the first step of the ladder. Sorry, the ladder is less likely to slide when the person is at the bottom rather than when he is at the top. So even if your intuition doesn't tell you this, it doesn't matter. The question itself implies that at a certain distance, beyond a certain distance, the ladder is going to slip, because we have to find the maximum distance the man can ascend without disturbing the equilibrium. So once again note, theta is not changing in this problem. It is tan inverse 1 upon 2 mu, where mu is the static friction coefficient between the ladder and the floor. So that's fixed. But what is changing is the fact that the man is climbing up, so his distance from point A is changing. So let's assume that finally the comfortable static equilibrium of the system changes into limiting static equilibrium. That is, the ladder is on the verge of slipping when the man is, let's say, at this point, somewhere over here. Okay, the man's weight is given to be W dash, so it acts through his CM, W dash, and we have to find what is this distance, which I'll call, let's say, D, such that the ladder is in limiting equilibrium. So one must understand very well which distance we are talking about. When we say the distance of the man from the bottom, the man himself has some non-zero dimensions. He has some width like this. So it's slightly ambiguous. From which point do we measure the distance from A to what point of the man? So we'll assume that when we continue this line, that is the line of action of W dash, is going to intersect the ladder, let's say at this point. So we are trying to find the distance between point A and that point. So that's the distance D. And of course now I have to draw the FBD of the ladder. Remember, the ladder is in limiting static equilibrium. The FBD will contain some of the forces which we have already shown in the previous question. So there will be NA over here. Likewise, there is going to be NB, the normal reaction here. And there's no frictional force here because the wall is given to be smooth. But there is limiting static friction at the bottom because of the condition of limiting equilibrium. It's in this direction. The NA is on the verge of sliding or slipping towards the right. So limiting friction, okay, and that's going to be mu times NA. So that's the complete FBD of the system. It's the FBD not only of the ladder, it's the FBD of the ladder plus man, the system consisting of ladder plus man. Now just to remind you yet again, theta is not any angle which you like. It is equal to tan inverse 1 upon 2 mu, because the question, I'll just repeat, the question states in the first sentence that the ladder before the man starts climbing rests against the rough floor and the smooth wall such that slipping impends. So the conditions of question number 10 are being recreated even before the man starts to climb. So naturally the angle must be the angle which we calculated in question number 10, and that's tan inverse of 1 by 2 mu. And once that is done, once the angle is fixed, then the man starts to climb. Okay, now just apply your normal force and moment equations. So the first thing that we can do is to apply the equation sigma Fy is equal to 0, which will tell you that my total downward force is W plus W dash, of course, that is equal to the upward force, that's equal to NA. So I'll just write it over here, mu NA is equal to W plus W dash, and immediately this mu NA becomes mu into W plus W dash. I'll just replace that. It's mu times W plus W dash. Then I can apply sigma Fx is equal to 0, and it means the rightward force must balance the leftward force. So NB is the rightward force. The only other force having a horizontal component is mu times W plus W dash, it's leftward. So NB must be mu times W plus W dash. I'll just replace NB with that, and of course the question asks us to find the value of D. So D is the distance between the man and point A. So obviously D has something to do with the placement of this particular force, and it means therefore that the line of action of W dash is going to be relevant in calculating the value of D, and therefore we must apply now the moment equation, because the line of action of a force is involved in the moment equations. So let's do that. So for example, we can take the moment about A and equate it to 0. The advantage of taking the moment about A is that there are two forces, this one and this one, which act through A, and therefore they won't appear in the moment equation. So I'll just create some place over here. Sigma MA is equal to 0. Sigma MA is equal to 0 because of the condition of static equilibrium. So let's begin by the moment of this force. It's going to turn the ladder in this direction about A, so that's clockwise. Let me assume, as usual, although it's not compulsory, let me assume that anti-clockwise is positive, and therefore this moment is going to be negative, and so it's going to be minus of, I write the force mu times W plus W dash, that's the magnitude of the force, and then I want to multiply by the distance between this line of action and point A, so obviously this distance, which is the same as this distance. And since I have assumed that the length of the ladder is L, it's L by 2 on this side and L by 2 on the other side, total length is L, therefore this relevant distance is going to be L times sine of theta. So accordingly you multiply this by L times sine of theta. Now let's go to this force W. W is trying to turn the ladder about A in the anti-clockwise direction, and so its moment must be positive according to our convention. So we have a plus sign plus W multiplied by, so it's the distance, the perpendicular distance between the line of action of W, which is this, and point A. In other words, we are talking about this distance. So if you consider this right angle triangle, the hypotenuse is L by 2 and the angle at the base, the bottom, is theta. So naturally this distance, the relevant distance, is going to be L by 2 times cos theta. L by 2 times cos theta. And now we go to the weight of the man, which is W dash. I'm going to get a similar moment about A. So the moment is going to be, once again you can figure out that it's going to be in the anti-clockwise direction once again. So I write plus W dash times, now the right angle triangle is a bit different, now it's the smaller right angle triangle, this one, and the hypotenuse is D, so it's going to be D times cos theta instead of L by 2 cos theta. The other forces do not contribute any moment about A because they pass through A, so this sum is equal to 0. Now I want to find the value of D, and since L is the only other length which is given in the question, in fact it is the only length which is given in the question, D is something we have to find, so we can expect that D is going to be in terms of L. So that is one expectation. Secondly, we realize that we have not really used this particular condition on theta, that is the value of theta is actually given as tan inverse of 1 by 2 mu. Now I do have mu over here and I have theta over here, so since mu and theta is here too, in fact it's also here, so rather than having mu as well as theta, a better approach would be to either express theta in terms of mu or mu in terms of theta, so that would make the equation less complicated. So what I can do is I can convert mu into theta. It's quite easy to do that. You just modify this particular equation, by taking the tan on both sides. You get tan of theta is equal to, now tan of tan inverse of 1 upon 2 mu. You just think over it, it turns out to be 1 upon 2 mu. So it's like doing two operations in reverse. So tan and then tan inverse, that's why you get 1 upon 2 mu. So just to give you an example, if you have not followed, you know that tan 45 degrees is equal to 1. So another way to express this is saying that 45 degrees is equal to tan inverse of 1. So if I ask you what is tan of tan inverse of 1, it's nothing but tan of, now what is tan inverse of 1? It is 45 degrees.
then you get back to the first equation here, so that's equal to 1. So this tan and this tan inverse, they seem to have they do have an opposite action, and when they follow each other, that is tan of tan inverse, then the answer is going to be this particular number which you write over here. So that's why tan of theta is written directly as 1 upon 2 mu over here. Now this implies that mu is 1 upon 2 tan theta, and one can even say it's cot theta divided by 2, and this value I'm going to substitute over here. So minus mu, I'm going to write minus of cot theta by 2, and let's see what happens then. So minus half into cot theta. Cot theta is cos theta over sin theta. I'll prefer to express it that way. Now you know that sin theta is not equal to 0. That would mean that theta is equal to 0. That's not true. So this sin theta is, you can cancel it. You can have it in the denominator in the first place because it's non-zero, and then further you can cancel it. So what that leaves us with is minus half cos theta. I'll just expand the bracket. Minus half of w cos theta, or wl cos theta, and there's another minus half w dash into cos theta, and of course it's multiplied by L. I forgot that. So that's the expanded form of this. I'll just replace it like that, and then you see that this term cancels with this term. Now do some rearrangement. You just take this term on the right hand side. Okay, so you get w dash multiplied by d cos theta equals half w dash multiplied by L multiplied by cos theta, and the cos theta term cancels, w dash term cancels. Okay, so you get d is L by 2, which means that when the man climbs up the ladder, the limiting equilibrium condition corresponding to the ladder being in the state of impending slipping, that happens when the man is at the midpoint of the ladder, which also means that the weights w dash and w pass through the same point. Now, does it mean that the man is safe in the lower part of the ladder, and then limiting equilibrium is reached at this point, and then he is unsafe in the upper part of the ladder, the upper half of the ladder, because the ladder will slip? Does it mean that, or does it mean the reverse? Does it mean that he is safe here, unsafe here, and here there is limiting equilibrium? So already we have discussed this in the very beginning. Our intuition tells us that he is safe in this region and unsafe in this region, and we can actually show it. In fact, in hindsight, one can actually solve this entire problem, question number 12, just in 1 or 2 minutes by thinking in a certain way. You must connect it with question number 10, and let's see, let me show you how that can be done. So let me just remind you of question number 10 again. So after solving the question, we came up with this sort of situation where this rod, it's a uniform rod, and the weight acts at the midpoint. So these two are equal, weight is W, and the rod is in limiting equilibrium. So what are the forces acting on the rod? W there's this normal reaction at the bottom. Now limiting equilibrium would mean there's limiting friction acting here. F limiting is equal to mu times NA, and here at this point you have the normal reaction at B, which is NB. That was the situation which we arrived at after looking at the problem, and of course we did find some values of some of the forces. For example, NB is going to be equal to whatever frictional force you have over here, and also the value of theta for limiting equilibrium turned out to be tan inverse of 1 upon 2 mu. So this was the sort of result that we got, or the end result of question number 10. Now just think for a moment, will this whole picture, will it change if the weight of this uniform ladder changes? If I bring this uniform rod changes, if I do the same experiment with a heavier rod, but everything else is the same, that is the value of mu is the same, for example, then don't I get the same value of theta? In that question we found what was theta finally, that was tan inverse of 1 upon 2 mu. It doesn't seem to depend on the value of W. If I had taken W1 in place of W, or W2, or twice W, that weight would anyway have not played any role in the evaluation of theta. Theta would still turn out to be tan inverse of 1 upon 2 mu. Now let's say that this uniform ladder doesn't have a weight W, but rather its weight is W plus some W dash. We don't know what is W dash, some W dash. I can always split the weight of the ladder. Suppose it's a ladder whose weight is 10 newtons. I can always say it's 7 plus 3 newtons. So who prevents me from saying that? So I've got a W and a W dash. The total weight is W plus W dash. It acts at the center, and still you have this situation where theta is tan inverse of 1 upon 2 mu. Now of course this NA, it's equal to W plus W dash rather than W now. This mu NA is therefore mu times W plus W dash, and of course NB is equal to that. NB is equal to F limiting itself by sigma Fx is equal to 0. Remember, this rod is in limiting equilibrium, so end point A is about to slip towards the right, and end point B is about to slip down. Now let's conduct a thought experiment in which the ladder, instead of being uniform, it becomes a non-uniform ladder. The rod, I mean. So for example, half of the rod, let's say half of the rod is made of wood and half of it is made of steel. So obviously the weight of the wooden part is much less, or is less than the weight of the steel part, so whatever weight you have, and naturally the resultant of these two forces can't act at the midpoint of the ladder. It's going to be in the lower section. Similarly it can be in the upper section. So that's what making the ladder uniform does. It shifts the weight W plus W dash away from the midpoint to some other point of the rod. Now when that happens, depending on whether W plus W dash shifts in this direction or in this direction, I will now show to you that the ladder is either going to be in comfortable equilibrium, meaning this limiting friction will now become static friction, comfortable friction, or in the other case the ladder will simply slip, it will lose equilibrium. So we can show that quite easily as follows. Let us say that W plus W dash acts at a lower position over here. The force is the same in magnitude, but rather than acting at this point, it's acting closer to A. Now, does the ladder remain in equilibrium? Let's figure that out. So the best way to do it, or at least one of the ways to do it, is to assume static equilibrium. Assume static equilibrium and then check for contradictions. The usual contradiction we check for is, we find the force required over here for static equilibrium, the frictional force, and then check whether that frictional force satisfies the equation, the inequality rather, Fs is less than or equal to mu times Na, because if it doesn't, it means that the required static frictional force is larger than the limiting frictional force, and so the ladder is going to slip. So that's the check, how we figure out whether the ladder remains in static equilibrium or not. So let's see what has happened. W plus W dash has moved nearer to A. Assume static equilibrium. Now Na is W plus W dash. That still remains even if the force W plus W dash has shifted nearer to A. That doesn't change. Now this F limiting, perhaps it becomes comfortable friction. We do not know. So let us check that. For that, we consider the moments about some point. In this particular at this phase, I do not want NA and NB to play any major role. So what I do is I just extend them. So these are the lines of action, and this is some point. I'll call it P. And I'll take the moments about P, because the moments about this total moment about P must be equal to 0. I know that. The moment about any point is 0, but particularly about P, NA and NB don't play any role. Now let's imagine, even before we shifted this force down, I'll just draw the picture again. So that was the situation. The force was at the midpoint and the total moment about P was still 0, which means the moment because of W plus W dash. So W plus W dash multiplied by this distance equaled mu into W plus W dash. That's the only other force which creates a moment about P is this force multiplied by this distance. Now what we have done is we have taken this force from here and put it over here, and we have still assumed static equilibrium. So the force W plus W dash now generates a smaller moment about P because its line of action has moved closer to P, and the moment which is balancing that is because of this force. We don't know whether it is F limiting. We can say it's F static because we have assumed static friction. Now that moment must balance a smaller moment. The first moment has become smaller. The two moments are in opposite directions. One of them is clockwise, the other is anti-clockwise. They must balance. Now one of the moments has become smaller in magnitude, so naturally this moment must also become smaller in magnitude. And the only way that that can happen is the force itself reducing. The force isn't going closer to P, so the force has to reduce, and therefore it's going to be not equal to mu into W plus W dash, but less than mu into W plus W dash. In other words, it's possible, there is no contradiction, because the required static friction is now it's within the limits. It's smaller than F limiting. Now that would mean that when you take the center of mass of the system, or the CG of the system, closer to A, then it's easier for the ladder to stay in equilibrium at this particular value of theta, because such a large frictional force is no longer required. You just require Fs, which is some Fs which is less than F limiting. You know that there is no contradiction elsewhere. For example, Na is equal to W plus W dash. That is still valid. It's going to balance the weight. And then if this is Fs, then this Nb, which was formerly equal to F limiting. Now it's equal to Fs. There is no problem there at all. NB can be equal to anything. It can be equal to Fs as long as it's a push, not a pull. A normal reaction can be a push, not a pull. So there doesn't seem to be any contradiction in taking the CG, the center of gravity or the center of mass, if you want, lower, that is towards A. In fact, the ladder is in comfortable equilibrium. Now obviously I'm sure you can figure out that if W plus W dash, instead of acting lower down, so let's take it back to its original position at the midpoint. Now from here let's take it up here. W plus W dash acts here. Now when I take the moments about P, if I assume static equilibrium first, then the moments about P must be equal to 0. What has happened is the moment because of W plus W dash has increased in magnitude, because this line has gone further away from P. This distance has increased from its former value. So that means that the moment coming from this F, whatever force is acting over here, I'll call it F, it's acting at this point, that moment has to increase, and the only way that can happen is the frictional force, the static frictional force, exceeds limiting friction. Now obviously that's a contradiction. F limiting is the maximum value of static friction, and therefore when the CG is in the upper half of the ladder, and under these conditions, for example when theta is tan inverse of 1 upon 2 mu and all that, surely the ladder is going to slip. When the CG is in the bottom half of the ladder or the rod, comfortable equilibrium, and the midpoint, when the CG is at the midpoint, it is limiting equilibrium. The ladder is on the verge of slipping. Now how is this relevant to our question, that is the question which we just did, question number 12. So here you see that instead of having a non-uniform rod of weight W plus W dash, you have a uniform ladder of weight W. W acts at the midpoint, and on that you have a man of weight W dash who is climbing. So if I consider the ladder plus the man to be a single system, then naturally W plus W dash is going to act somewhere in between, somewhere through this line, W plus W dash. And as the man starts from the bottom, as the man climbs higher and higher, as he approaches W, what will happen is, not only does this force approach this force, that is it goes closer and closer, but the resultant W plus W dash will also climb higher and higher until it acts at this point. That will be when the man is standing at the midpoint of the ladder. So when the man is ascending the lower part of the ladder, it essentially means that the force W plus W dash, it's acting somewhere here, maybe in the beginning, and then it goes up, and then finally it reaches this point. So naturally it means, if you compare it with the question, the thing that I just did right now, it means that the system is going to be in comfortable equilibrium when the man is in the lower half of the ladder, until the man reaches the midpoint of the ladder, when the system reaches limiting equilibrium, it's on the verge of slipping. And the moment the man goes to the left or higher up, so that means that W plus W dash is going to act somewhere over here, and naturally from the discussion that we just had, it means that the ladder will slip. So this entire question number 12, which actually just asks you what is the maximum distance a man of weight W dash can ascend the ladder without disturbing its equilibrium, can be solved by an analogy of taking this sort of non-uniform ladder. Once you have solved question number 10, then you convert the ladder into a non-uniform ladder of weight W plus W dash. Then you change the position of the CG, and you realize that when the CG is is in the lower half, the ladder is in comfortable equilibrium. At the center, it's in limiting equilibrium. In the upper half, the ladder will actually lose equilibrium. You can solve question number 12 just by this simple analogy if it strikes you. So this completes our discussion on question number 12. The next question we will attempt in this screencast is question number 14 in the extra class worksheet on friction. So let's read the question. A block B whose weight is 80 newtons rests on another block A whose weight is 160 newtons. An ideal string, this one, passes around a frictionless pulley to connect both these blocks. So you can see that the ends of the string are connected here and here to the two blocks. What would be the minimum value of the horizontal force P to drag the block A towards the left? And mu has been given to be 0.25 for all sliding surfaces. Now since mu s and mu k, the static and kinetic coefficients of friction, are not given separately, we assume that both of them are individually equal to 0.25. Mu s is equal to mu k is equal to 0.25. So we want to find what is the minimum force P minimum, to start this system moving. Now you must visualize how will the system move. When you apply the minimum force or something larger than the minimum force over here, then block A will actually move towards the left and block B will slide on top of block A, and to an observer on the ground, block B will appear to move towards the right. Now another thing to note is, even in the reference frame of A, so I attach a reference frame to A like that X and Y axis I am showing here. Even to such an observer attached to this reference frame, B will still appear to be moving towards the right, because B is essentially going to reach at some stage this particular position. It's trying to go towards the right end of block A, and we want to find the minimum magnitude of P which will do the job. Now as we have done often before in the class, we convert this dynamics problem, in which we want to get the system to move, into a statics problem. So instead of finding the minimum value of P which can actually move the system, we find the maximum value of P for which static equilibrium exists. So imagine that you don't apply any force P to begin with. The system is in equilibrium. The strings are assumed to be straight, and you now apply this force P, gradually go on increasing it until A is about to slide. It's not actually sliding, but it is on the verge of sliding towards the left, and B is on the verge of sliding with respect to A towards the right. So this is the situation which we have to investigate. It is a situation of static equilibrium, because motion is still not occurring. Motion will not occur. It's a limiting case of static equilibrium. So as long as you continue applying this same force P max, it's the maximum force for static equilibrium, and so it reduces to a problem of static equilibrium, and in particular limiting static equilibrium. So we have to actually draw the FBDs of the two blocks separately we could try drawing the FBD of block A and B together and see whether that works. But I will show you how to solve the problem by drawing A and B's FBD separately. Now the pulley and the string, these are given to be ideal. So that would mean that in the FBDs, the tension which the string applies on block B, let's call it T, the same tension prevails at the other end too. The tension remains the same. That's a property of an ideal pulley and string system. So this fact we will make use of when we are drawing the two separate FBDs. Remember, the FBDs are drawn for the case of limiting equilibrium. So let's first draw the FBD of block B under these limiting equilibrium conditions. Now the weight of block B has been given to be 80 newtons, and the other force acting on this block is the tension in the string, that's T in this direction. The normal reaction that is applied by A on B, that must definitely balance 80 newtons because this block B doesn't move up or down. So that's going to balance it. The normal reaction, I'll call it N1, 80 newtons. And the frictional force is a limiting frictional force. So its value must be mu times N1, and that's 0.25 multiplied by 80. Now that's 20 newtons. The frictional force applied by A on B is 20 newtons, and because in the reference frame of A, B seems to be, well, it has a tendency to move towards the right with respect to A. So because of that, the limiting frictional force is towards the left. So I'll call it F limiting. It's 20 newtons. It's towards the left. Now one small point, not too important in this problem, but you see that this T and this 20 Newton, they're going to be equal, of course, because sigma Fx is equal to 0. So they form a couple in this direction, and therefore these two equal forces must constitute a couple in the opposite direction. And so I've shown N1 not in the same line of action as 80 newtons as the weight, that is, but slightly towards the right. So that's just a small point which may not be very important in this problem. It will be important if we are evaluating the moments of these forces, because the line of action becomes important then. Otherwise it's not too important. Now sigma Fx is equal to 0, as I just said. It implies that T equals 20 newtons. Go to the other block and draw its FBD. The FBD of block A. So here the block is here. The block weighs 160 newtons, and the tension in the string, the same tension acts, so it's the same tension as this. It's going to be 20 newtons. T equals 20 newtons. Now these two forces are forces applied by A on B. They are contact forces, friction and normal reaction. So by Newton's third law, the same forces act but in an opposite direction on the lower block, on A. So the normal reaction exerted by B on A is once again 80 newtons. I'll have to show it. There's no place to the right of this arrow, so I'll show it towards the left. It doesn't matter. So N1 is 80 newtons. So actually, if I draw the blocks A and B exactly in the relative positions with respect to each other, then this N1 and this N1 must be in the same line. They must be collinear. They are an action and reaction pair. But it doesn't really matter in this particular problem. So that's N1. The other force acting is limiting friction exerted by B on A, and that must be the same as this but in the opposite direction. So it's this over here, F limiting, that's equal to 20 newtons. Now the normal reaction from the ground, of course it must balance the sum of these two forces, 80 newtons and the weight 160 newtons. That's by sigma Fy equal to 0. So this normal reaction I'll call it N2, and of course because sigma Fy is equal to 0, it must be 80 plus 160, that's 240 newtons. If you want, you can show the arrow a bit bigger, because technically speaking it must be bigger than the arrow corresponding to 160 newtons. And there's one force which is left, that is the friction exerted by the ground on block A at the bottom, and you have to place, in fact there is another force, there's P also, so we can write P max, and the force that I was just talking about is the frictional force exerted by the ground on block A at the bottom. So just place yourself in the reference frame of the ground, imagine you are in that reference frame. So with respect to the ground, the block A is on the verge of moving or sliding towards the left, and naturally the frictional force is limiting frictional force towards the right. So I'll just draw it over here. It's limiting frictional force, so F dash limiting, let's call it, and that's mu times normal reaction. So once again 0.25 is the value of mu. The normal reaction is 240 newtons, so that's going to be 60 newtons. F limiting is 60 newtons. F dash limiting is 60 newtons. Now just apply the equation sigma Fx equal to 0 to block A, and what you get is the leftward force P max must equal the rightward force. So F limiting at the top, that's 20 newtons, plus the tension 20 newtons, plus F dash limiting at the bottom, that's 60 newtons. So the answer is 100 newtons. So this is the maximum force which you can apply on A, the maximum value of P for static equilibrium, and which means that the minimum value of the force P to actually start the motion is actually, it's a bit more than 100 newtons, but the convention is to write it as 100 newtons itself. So that's the answer of question number 14.